The manufacturing lines went quiet at 3:47 a.m. Eastern Standard Time. Not because of a power outage, not because of a labor strike, not because of regulatory intervention. The silence came from something far more fundamental, something that transforms how we understand the relationship between advanced technology and the materials that make it possible. While financial markets focused on quarterly earnings and central bank announcements, a different kind of calculation was taking place in procurement departments across 3 continents. Engineers were running numbers that hadn't been run before. Supply chain managers were making phone calls to sources they hadn't contacted in years. And quietly, without fanfare or press releases, purchase orders were being rewritten. This wasn't a disruption anyone would see on a chart, but it was one the system would eventually have to price. This discussion is for educational and analytical purposes only, and does not constitute financial advice. What happened in those early morning hours represents more than a shift in industrial planning. It suggests we have crossed a threshold where the physics of materials begins to override the assumptions of finance, where the constraints of geology start to dictate the possibilities of technology, where the gap between laboratory breakthroughs and industrial reality becomes impossible to ignore. The story begins not with price charts or market sentiment, but with a fundamental change in how certain materials are consumed, not used, consumed. The distinction matters because usage implies temporary interaction. Consumption implies permanent transformation. And when a material transitions from being used to being consumed, everything about its market dynamics changes. The technology responsible for this shift has been discussed in research papers for years. Academic journals have published detailed studies on its potential. Industry conferences have featured presentations on its theoretical applications. But theory and implementation exist in different universes, and the gap between those universes has been closing faster than most people realize. What makes this particular technological advancement significant is not its complexity, but its simplicity. The breakthrough doesn't require exotic materials or revolutionary manufacturing processes. It relies on something much more basic, something that has been available for centuries but never consumed at the scale this technology demands. The material in question has traditionally played a supporting role in industrial processes. A coating here, a conductor there, small quantities distributed across thousands of applications. Its primary characteristic has been its reliability in small doses, its conductivity, its resistance to corrosion, its ability to facilitate chemical reactions without being consumed by them. These properties made it valuable but not critical, useful but not essential. That relationship has fundamentally changed. The technological breakthrough that emerged from materials science laboratories over the past 18 months doesn't just use this material. It incorporates it as a structural component. Not as a catalyst that facilitates a reaction and remains unchanged, not as a coating that provides surface protection, but as an active participant in the core function of the technology itself. This transformation from catalyst to component represents a phase transition in how the material relates to modern manufacturing. The quantities required increase not incrementally, but exponentially. The applications shift from optional enhancements to mandatory requirements. The economics change from cost optimization to supply security. Understanding this shift requires examining the chemistry involved. The technology works by creating what researchers call a stabilization matrix. Think of it as a molecular scaffold that prevents certain unwanted reactions while enabling others. The material serves as both the foundation and the regulator of this matrix. Without it, the technology simply doesn't function. Previous attempts to create similar technologies failed because they relied on alternative materials that couldn't provide the same level of control. Silicon-based approaches proved too volatile. Polymer solutions degraded under operational conditions. Ceramic matrices couldn't achieve the necessary conductivity. The breakthrough came when researchers realized that only one material possessed the exact combination of properties required. The implications extend far beyond the laboratory. This technology addresses a fundamental limitation that has constrained an entire industry for decades. It solves a problem that has forced compromises in design, performance, and safety. And it does so in a way that makes those compromises unnecessary. But solving the technical problem creates a different kind of problem, a materials problem. Because while the technology can be scaled, the material it requires cannot be manufactured. It must be extracted, refined, and processed. And the infrastructure for doing that at the scale this technology demands simply doesn't exist. Current global production of this material serves existing applications adequately. Electronics manufacturing, solar panel production, medical devices, automotive components. These industries have adapted their processes around the available supply. They design products that use minimal quantities. They engineer solutions that maximize efficiency per unit of material consumed. The new technology disrupts this careful balance. Conservative estimates suggest it could increase demand for this material by 200 to 300% within 5 years. Moderate scenarios project increases of 400 to 500%. Aggressive adoption models indicate demand could increase by 800 to 1,000%. These aren't gradual increases that supply chains can accommodate through normal expansion. They represent step function changes that require entirely new approaches to sourcing, processing, and allocation. To understand the magnitude of this shift, consider the numbers. Current annual global production of this material totals approximately 800 million ounces. Existing applications consume roughly 750 million ounces, leaving a buffer of 50 million ounces that flows into strategic reserves and investment holdings. If the new technology achieves just 10% market penetration in its target applications, it would require an additional 150 to 200 million ounces annually. That would eliminate the buffer entirely and create a structural deficit. At 25% penetration, the technology alone would require more material than current total global production. At 50% penetration, total demand would exceed 1.3 billion ounces annually, requiring a 60% increase in global production capacity. These calculations assume conservative material loading per unit. If actual consumption proves higher than laboratory estimates suggest, the numbers become even more challenging. The supply response to such demand increases follows predictable patterns, but those patterns operate on geological timelines, not technological ones. Discovering, developing, and bringing new production capacity online typically requires 8 to 12 years. The lead times are built into the physics of extraction and the economics of capital deployment. Existing mines cannot simply increase output proportionally. Most operate near capacity already. Those with expansion potential face constraints related to water availability, energy costs, labor availability, and environmental regulations. Meaningful capacity increases require major capital investments that mining companies have been reluctant to make given the historical volatility of commodity prices. The geographic concentration of production adds another layer of complexity. 3 countries control approximately 65% of global production capacity. 2 of those countries have recently implemented export restrictions or additional royalty structures that effectively increase the cost of international supply. The third faces ongoing infrastructure challenges that limit the reliability of shipments. This geographic concentration means that supply disruptions in any one region can affect global availability. Political instability, labor disputes, transportation bottlenecks, or natural disasters can create temporary shortages that ripple through entire industries. Recycling represents a potential source of additional supply, but one that operates under different constraints. The material can be recovered from end-of-life products, but the recovery process is complex and often uneconomical at small scales. Most recycling focuses on applications where the material is highly concentrated, such as jewelry or specialized electronic components. The new technology presents a recycling paradox. While it consumes larger quantities of the material per application, that material becomes embedded in products with longer useful lives. Solar installations operate for 25 to 30 years. Industrial equipment functions for decades. The material consumed today by this technology won't return to recycling streams until the 2050s. This creates what material scientists call a sequestration effect. The material flows into applications where it remains locked away for extended periods, reducing the recycling supply available to meet near-term demand increases. Historical precedents suggest that when new technologies create sudden increases in materials demand, markets initially respond with price volatility rather than supply expansion. The volatility reflects the tension between immediate needs and supply constraints that can't be resolved quickly. During the early phases of such transitions, financial markets often lag behind physical realities. Pricing mechanisms designed for steady-state conditions become unreliable when underlying demand patterns change abruptly. The gap between paper prices and physical availability can persist for months or years until new equilibria emerge. This lag creates opportunities for misallocation and mispricing. Industries that depend on the material for existing applications may find themselves competing with new applications that can absorb much higher costs. Financial instruments designed to hedge normal price movements may prove inadequate when structural demand shifts create new volatility patterns. The psychological dimensions of such transitions often prove as important as the physical constraints. Market participants accustomed to gradual changes struggle to process discontinuous shifts. The tendency is to interpret new information through the lens of past experience, even when past experience provides poor guidance for current conditions. Skeptics typically point to several factors that could limit the impact of such technological shifts. They note that laboratory breakthroughs often fail to achieve commercial viability. They observe that manufacturing scale-up frequently encounters unexpected obstacles. They emphasize that cost considerations may prevent widespread adoption. These concerns deserve serious consideration. Historical data indicates that fewer than 20% of laboratory innovations successfully transition to commercial production. Of those that do, fewer than half achieve the market penetration initially projected. Scale-up challenges, regulatory obstacles, and competitive responses can all limit the ultimate impact of new technologies. However, the current situation differs from typical innovation patterns in several important ways. The technology addresses a well-documented limitation that constrains a large, established industry. The economic benefits of adoption are substantial and clearly measurable. The technical risks have been largely resolved through extensive testing. And most significantly, major industry participants have already committed capital to implementation. Purchase orders have been signed. Manufacturing capacity has been allocated. Supply agreements have been negotiated. These commitments represent more than intentions or hopes. They constitute binding obligations that create demand regardless of market conditions or price movements. The structural changes are already influencing real-world decisions, even as public pricing mechanisms continue to reflect historical supply-demand relationships. Procurement strategies developed over decades are being rewritten. Long-term contracts are being renegotiated. Strategic reserve policies are being reconsidered. The gap between emerging physical realities and existing financial frameworks suggests we are in the early stages of a materials transition that will reshape multiple industries. The constraints imposed by geology and chemistry are beginning to override the assumptions of economics and finance, and the adjustment process, while inevitable, will likely prove neither smooth nor predictable. Able. The conversations happened during lunch breaks and after hours, in conference rooms with whiteboards covered in calculations that weren't meant for quarterly reports. Engineers drawing diagrams that looked more like molecular structures than profit projections. Procurement managers pulling up supplier databases that hadn't been accessed in months. And in those quiet moments between meetings, the realization began to settle that the assumptions underlying entire industries might need fundamental revision. The shift didn't announce itself through market volatility or breaking news alerts. It emerged through technical specifications being quietly updated in manufacturing facilities across different continents, through revised material requirements appearing in purchase orders, through supply chain managers suddenly asking questions about availability rather than price, the kind of questions that suggest someone has done calculations that change how they think about the future. This discussion is for educational and analytical purposes only and does not constitute financial advice. What these conversations revealed was not a gradual evolution in industrial processes, but something more fundamental. A threshold had been crossed where the physics of materials began to impose constraints that financial markets hadn't yet recognized, where laboratory breakthroughs had achieved sufficient commercial validation to trigger procurement decisions, where the gap between theoretical possibility and practical implementation had narrowed to the point where real capital was being committed to real production schedules. The technology at the center of these conversations represents a solution to a problem that has constrained entire industries for decades. Not an incremental improvement, but a fundamental reimagining of how certain processes can function. The breakthrough doesn't rely on exotic materials or revolutionary manufacturing techniques. Instead, it achieves its effectiveness by incorporating a familiar material in an entirely new way. This distinction matters because it changes the relationship between the technology and its material requirements. Previous approaches treated materials as inputs to be minimized through efficiency improvements. The new technology treats one specific material as a structural component whose presence determines whether the system functions at all. The material in question has served industrial applications for centuries. Its properties are well understood. Its behavior under various conditions has been extensively documented. Its role in existing technologies is established and reliable. What changed was not the material itself, but how it gets incorporated into the new technological framework. Traditional applications use this material as what chemists call a catalyst or facilitator. It enables reactions without being consumed by them. It provides conductivity without degrading over time. It offers corrosion resistance while maintaining other desirable properties. These applications typically require small quantities distributed across many components. The new technology fundamentally alters this relationship. Instead of using the material as a catalyst, it incorporates it as what researchers term an active matrix component. The material doesn't just enable the technology to function, it becomes part of the technology's core architecture. The quantities required increase not proportionally with system size, but exponentially with performance requirements. Laboratory testing confirmed what theoretical models had suggested. Alternative materials couldn't achieve the same level of performance. Silicon-based approaches proved unstable under operational conditions. Polymer solutions degraded too quickly. Ceramic composites couldn't provide the necessary electrical characteristics. The breakthrough came when researchers realized that only this specific material possessed the exact combination of properties the technology required. The chemistry involves what materials scientists describe as a stabilization network. The material creates a three-dimensional structure at the molecular level that prevents unwanted chemical reactions while enabling desired ones. This network must maintain its integrity under varying temperature, pressure, and electrical conditions. The material serves simultaneously as the network's foundation and its regulatory mechanism. Understanding the technical requirements helps explain why demand projections for this material have been revised upward repeatedly over the past 18 months. Initial estimates assumed the technology would use quantities comparable to existing applications. As testing progressed, engineers discovered that performance scaled not linearly with material loading, but according to more complex mathematical relationships. Conservative loading estimates now suggest the technology requires between 10 and 15 times more material per application than originally projected. Moderate estimates indicate the requirement could be 20 to 25 times higher. Aggressive performance targets might require 50 to 100 times more material than initial calculations suggested. These revisions have profound implications for global material balances. Current worldwide production totals approximately 800 million ounces annually. Existing applications consume roughly 750 million ounces, leaving a buffer of 50 million ounces for strategic reserves and other uses. If the new technology achieves 10% market penetration in its target applications using conservative loading estimates, it would require an additional 120 to 180 million ounces annually. This would eliminate the existing buffer and create a structural deficit of 70 to 130 million ounces. At 25% market penetration, the technology alone would require 300 to 450 million ounces annually, pushing total demand to between 1.05 and 1.2 billion ounces. This represents a 30 to 50% increase over current total global production. At 50% penetration with moderate loading assumptions, total demand could reach 1.4 to 1.6 billion ounces annually, requiring a doubling of global production capacity. These calculations assume loading requirements remain within current engineering estimates. If actual consumption proves higher than laboratory testing suggests, the numbers become significantly more challenging. The mathematics become even more complex when adoption timelines are considered. Historical data indicates that transformative industrial technologies typically achieve 10% market penetration within 3 to 5 years of commercial introduction, 25% penetration within 5 to 8 years, and 50% penetration within 8 to 12 years. The new technology has already progressed beyond laboratory validation. Pilot production facilities are operational. Commercial partnerships have been announced. Manufacturing capacity is being allocated. The timeline for meaningful market penetration appears to be accelerating rather than following historical patterns. This acceleration creates what supply chain analysts call a compression effect. Demand increases that might normally unfold over decades could occur within years. Supply chains optimized for gradual growth face sudden step function changes that exceed their adaptive capacity. Mining operations cannot respond to such demand increases quickly. Discovering, permitting, developing, and bringing new production capacity online typically requires 8 to 15 years. The timeline is constrained by geological realities, regulatory processes, and capital deployment cycles that operate independently of technological innovation or market demand. Existing mines face their own expansion constraints. Most operate near current capacity limits. Those with expansion potential encounter obstacles related to water availability, energy costs, skilled labor shortages, and environmental compliance requirements. Meaningful capacity increases require major capital investments that mining companies have historically been reluctant to make given commodity price volatility. The geographic distribution of production capacity adds additional complexity. 4 countries control approximately 70% of global production. 2 have recently implemented export restrictions or additional taxation structures that effectively increase international supply costs. 1 faces ongoing infrastructure challenges that limit shipment reliability. The 4th maintains stable policies but operates at near capacity already. This concentration means that supply disruptions in any major producing region can affect global availability. Political instability, labor disputes, transportation bottlenecks, natural disasters, or policy changes can create temporary shortages that propagate through interconnected supply chains. Recycling represents a potential source of additional material supply, but operates under different constraints and timelines. The material can be recovered from end-of-life products through established processes. However, recycling economics depend heavily on material concentration and recovery efficiency. The forces set in motion during those quiet morning hours in manufacturing facilities across 3 continents suggest that market mechanisms designed for incremental change may prove inadequate when confronted with structural transformation. The gap between laboratory validation and industrial implementation has collapsed faster than supply chains can adapt. Purchase orders have been signed that commit capital to production schedules extending years into the future. These aren't expressions of optimism or speculation. They represent binding obligations that create demand regardless of price movements or market sentiment. The physics of materials has begun to impose constraints that financial frameworks struggle to process, and the adjustment period ahead will likely test the assumptions underlying decades of industrial planning. When geology and chemistry start dictating the boundaries of technological possibility, the systems built around different assumptions must eventually yield to new realities.